All right, so I wanted to follow up on a few things from last week. So there were a few proofs that I went over that were not very well written, in my opinion, both in the book and in my notes. So I wanted to follow up on that. So first of all, I also wrote an email about it, so maybe you saw the email. So first of all, there were a few results we discussed about unipotent groups. Okay, and I'll adopt the same notation that we had before. So U sub n is the subgroup of GLN consisting of upper triangular matrices with ones along the diagonal. And we had some results, but I want to prove this result. So if we have a linear algebraic group that's unipotent, so that means all the elements are unipotents, and its only finite dimensional irreducible representations are the trivial one. So any finite dimensional irreducible representation has to just be the trivial representation. So I won't go through the proof in detail since it uses some ideas we already saw, but let me kind of set things up. So if we have a finite dimensional representation, and it's irreducible, then we can use, so I should have said here, finite dimensional irreducible representation. Then we can use this tool that we saw in the proof of 2.4.12 with Burnside's theorem on matrix algebras and the non-degeneracy of the trace pairing to argue that the image of this homomorphism inside GLN is just trivial, it's just one. Again, V is actually irreducible. So if we have a irreducible representation where the action of G factors through the trivial group, including inside of GLV, then it must be the one-dimensional trivial representation. So that shows this result. So you can see this argument with Burnside's theorem and the trace pairing in the book. But I wanted to isolate this specific result. And then just a remark. So if we have a finite dimensional representation of a unipotent group, we know that it's only irreducible if the representation is trivial, but it could be still indecomposable. So it could be the case that it could be the case that there are no irreducible. There's no invariant subspace with a complement. So there's no direct sum decomposition of V into two subrepresentations, non-trivial proper subrepresentations. So, for example, if we had UN, that's a unipotent group, and it has a natural action on k to the n, given by just the usual inclusion inside of matrices. And that is in general not irreducible. For example, the first basis vector is always, the span of the first basis vector is always a subrepresentation, but it's indecomposable. We can't break it up into a direct sum of smaller representations. Okay, and then with this proposition in hand, we can prove the original claim that if G is a subgroup of GLN consisting of only unipotent matrices, then we can conjugate it so that it's a subgroup of UN. And the proof is similar to what we saw. So if except for the induction step. So we proceed by induction on n. So n is the size of the GLN that we're embedding into. If n is equal to 1, then there's nothing to show since the only unipotent element of GL1 is 1. And if G is a subgroup of GL1 consisting of unipotent matrices, then it's just a trivial group. So if n is bigger than 1, then we know that the action must be reducible, that there's some invariant subspace of the action of G on V. V is just k to the n. We know this by the previous proposition. And so then we consider the action of G on this invariant subspace and on G mod and V mod W. So yeah, you can go through and yeah, it's similar to some arguments we've already seen, so I didn't spell out the details here. Okay, so that hopefully clarifies the picture a little bit. I think that's all I had. Yeah, that's all I had to say about unipotent groups. Does that make sense? Is it maybe a bit clearer than what we saw before? Are there any questions about this? Okay, I guess it's good. So we also saw some results about commutative groups. What I want to go through again is the proof that any connected linear algebraic group of dimension 1 is commutative. I'm using the same ideas as in Springer, but I'm just reformulating them in a way that's clear, at least to me, hopefully to some of you too. So first of all, this will be my notation for conjugacy classes. So if we have any algebraic group and an element little g in the algebraic group, then the conjugacy class is all the conjugates of G by elements in capital G. Okay, so here's what we want to show. So if let's say G is a connected linear algebraic group of dimension 0 or 1, then if the closure of a conjugacy class of some conjugacy class is equal to all of G, then G has to be the trivial group. So I'm just going to give the sketch of the proof since we went over some of these ideas in more detail last time. So if we suppose that the closure of a conjugacy class is equal to the whole group, then the fact that the dimension of G is less than or equal to 1 implies that the complement is finite. So the complement of this conjugacy class within G is finite. So that's true for any. That's true quite generally. I guess we're using the fact that the closure of CG is an irreducible, closed irreducible subvariety of G. Yeah, okay, and then we embed G inside of GLN, and we use this characteristic polynomial map. So we know the characteristic polynomial map is invariant under the conjugation action. So it's constant on this conjugacy class CG. And there's these finitely many other points. So there's only finitely more possibilities for the characteristic polynomial. And we can conclude that it has finite image. So we restrict it to this subgroup G, and we see that it has to have finite image. Since it's a continuous map, and G is connected, we see that in fact the image must consist of a single element. What element is that? Well, that must be the characteristic polynomial of the identity. So we know that the group has identity and its characteristic. So by this argument, every element in G has the same characteristic polynomial as the identity. And we also, when we talked about the Jordan decomposition and unipotent matrices and so forth, we saw that unipotent matrices are exactly those that have 1 as their only eigenvalue, as the only root of the characteristic polynomial. So that means that every element of G has the same eigenvalues as the identity. By 2, we conclude that every element of G has the same eigenvalues as the identity. So it must be that every G is unipotent. And then we use the fact that when we take successive commutators of the inside the UN or inside of any subgroup of UN, then we must be getting something smaller. And eventually these successive commutators reach just the trivial group 1. In particular, for in the case that we're interested in, so this is called the derived series. These successive commutators, we know that the commutator of G, so brackets G comma G, must be smaller than G, must be a proper subgroup, And because the dimension of G is at most 1 and the commutator is connected, the only possibility is that this commutator is trivial. Okay, and then commutator being trivial implies the following. So if we have our little g, and it's contained in its conjugacy class, and its conjugacy class is, we can write it in this way, so we just put a g inverse g in front. It doesn't really change anything, but the advantage of writing it this way is that we see that the g times the conjugacy class of g, so this subset of the group, is contained inside the commutator, because anything in the conjugacy class is xg x inverse, and maybe I should have written, yes, sorry, it should be in the other order, g inverse. And then so then everything in g inverse times the conjugacy class is g inverse x g x inverse, so that's the commutator, so it's contained in here. The commutator is trivial, so this is we get just a singleton g, and since and finally, since the closure of this conjugacy class is all of G, we see that the only possibility is that G is the trivial group. Okay, so now that we have proved this lemma, we can prove the proposition. So if we have something that's connected linear algebraic group G of dimension 1, and we have an element little g in G, then we have to argue that the conjugacy class of that element is just itself. And that's enough to prove the theorem, because if that's true for all elements in G, then the group must be commutative. Because, so that's just group theory. So how do we prove this? So G is not trivial since it's dimension 1. So that means that the closure of every conjugacy class, in particular this one that we've chosen, the closure of this conjugacy class must be proper in G. But since the closure is an irreducible closed subset of G, so it's connected, and G has dimension 1, so this must have dimension smaller, so it must be of dimension 0. And since it's connected, since the group is connected, so it refers to, since the conjugacy class is connected, we have to have that it's just one single point. So it's something connected of dimension 0. So it must be just a single point. We know it contains little g, so it must be just little g. And that's what we wanted to show. Okay, so I wanted to mention just one more result in this direction. We won't prove this result in full, but let me say a few things. So if we have a linear algebraic group of dimension 1, then by what we just, I guess maybe we also need connected. By what we just proved, it must be commutative. And in fact, more is true. It must be isomorphic either to the multiplicative group or to the additive group. And so we won't prove this theorem in full, but we will show that if all elements are semi-simple in the group, then it must be the multiplicative group. And what we showed last time is that that G must be either equal to its set of semi-simple elements or to its set of unipotent elements. And if it's equal to the set of semi-simple elements, then what we'll show maybe even later today is that it must be isomorphic to the multiplicative group. And in the latter case, we need some more machinery to show this, and but we'll not go through the proof in this class. You're welcome to take a look at sections 3.3 and 3.4 for more details about the proof of that part. All right, so this seems like a lot of stuff, but I think we went over some of these things already last week, so there's not that much new content. It's just kind of reformulations.
May I ask a question?
Sure, yeah.
Is it possible to derive this kind of theorem from knowing that we can embed G inside GLN and having some bound on the n in which we can embed, and then just going over the one-dimensional subgroups there?
Um, so thinking about G as a one-dimensional subgroup of GLN, um, I think I mean, okay, for the, let me think. So I'm more familiar with the proof where in the case where everything is semi-simple. So that's the first step of the proof where everything is semi-simple, and then you go from there. So, and for that case, the answer, I guess, is yes to your question. In the other case, I'm not so familiar with that proof, but I think the first step is again to embed G inside of GLN. And then since it's commutative, it'll land inside of UN, and you go from there. So I think yeah, I think so. Actually, maybe this is yeah. So now I'm remembering. So the way the proof goes is you prove that UN is an extension of additive groups of GAs, and and then there's some more steps, and you conclude that it's GA. So yeah, so I mean, I'm not sure exactly what your question is, but it's definitely, the proof of this theorem definitely uses the embedding property for linear algebraic groups. Does that answer your question? Or?
I was specifically interested in whether we can bound the n, get our bound on the n in which we can embed, and then use it to just go over all the cases. But maybe even without having a bound, it's still easy enough.
Yeah, I think so. Yeah. Yeah.
Okay. Thank you.
No problem. Any other questions? Okay. So let's move on then. Yeah. Okay, so the next topic we want to cover is about, so we just talked a little bit about commutative groups. So there's a certain class of commutative groups that are kind of fundamental to the subject, and they're relatively easy to understand. So we'll basically cover many of the major results about these commutative groups today. So, okay, so what is this class of groups? So a linear algebraic group is called diagonalizable if it's isomorphic to a closed subgroup of some number of copies of the multiplicative group. And it's called a torus or algebraic torus if it's isomorphic to some number of copies of the multiplicative group. Okay, so okay, just for later purposes, if n is equal to 0, then we have the trivial group. And the reason that these groups are easy to understand is because there's a dictionary between diagonalizable groups and finitely generated abelian groups. So in a group theory class, you learned about finitely generated abelian groups and the classification theorem and structure theorem for such groups. And under this dictionary, the multiplicative group, which is the simplest diagonalizable group, just corresponds to the integers. And the way we define this dictionary is by taking characters. So that's what we'll talk about next. So what's a character? Well, if we have a linear algebraic group G, then a character is just a homomorphism to GM. So to the multiplicative group. So it's a homomorphism of algebraic groups. And the notation for the set of all characters of G is the following. So capital X star up here of G. So it's yeah, it's the star is to denote that this is some sort of dual space. It's not really the exact same thing as duals in vector spaces, but it's some way of understanding G through maps to GM. Okay, so that's a character, and a co-character is it's kind of the dual notion. So a co-character is also known as a multiplicative one-parameter subgroup, and it's a homomorphism from GM, from the multiplicative group to G. And the set of co-characters is X and then a star in the bottom, subscript star of G. Okay, so those are pretty basic definitions. Okay, some remarks about these definitions. First of all, if we have any linear algebraic group, then its characters form an abelian group. So first of all, the characters belong to the affine algebra functions on G. And they form an abelian group, and we write this abelian group additively. So chi1 plus chi2 evaluated at G is the product of chi1 and chi2 each evaluated at G. And this is commutative because this product is happening in GM in the multiplicative group, which is commutative. All right, and now if G is commutative, so this is only true. So when I first wrote the notes, I needed to go back and add this. So the co-characters form an abelian group, but only if G is commutative. And we again write this abelian group additively. So lambda 1 plus lambda 2 evaluated X. So X here is an element in the multiplicative group, is the product of lambda 1 and lambda 2, each evaluated at X. And why is this abelian? Well, because that's where we need the G is commutative, so that the order here doesn't matter. Okay, so those are the definitions of characters and co-characters. So what are some examples? Well, first, the easiest example is the multiplicative group. So in this case, a character is just a homomorphism from GM to GM, group homomorphism, algebraic group homomorphism. And we saw previously, so we proved this result, that any algebraic group homomorphism from GM to GM is just given by an integer. So it's given by taking x to the n for some integer. And so that means that the character, the group of characters is just a group of integers. And similarly, if you compute the co-characters of GM, then you do the same thing. You write out the same thing, and you get the integers. All right. So what about if we take copies of GM? Well, if we take n copies of GM, then what we get is then what we need to compute for the characters are group homomorphisms from GM to the n to GM. But now this HOM commutes with finite finite products or co-products. They're the same in this with groups. And so then this is the same as n copies of the homomorphisms, group homomorphisms from GM to GM. And that just, so we know that this is just integers, so that's a z to the n. So if we want to be a bit more explicit, then there's a z basis for this character group, and it's given by just projection onto the ith coordinate. So chi I is projection onto the ith coordinate. That's a character, and these give us any character is a z linear combination of these. Okay, so and one thing to observe here is that that these characters, these chi i's, if we have these chi i's, they generate the algebra, the chi i's together with their inverses, I guess. they generate the affine algebra of GM to the n. And if we look at all the characters, so all the z-linear combinations of the chi-i's, then we get a basis for this affine algebra. So that's an important fact. So a general element in this affine algebra is something complicated, but it turns out that we can always write it as a linear combination over the ground field K of characters.
Is this something you didn't prove this, right? It's just a fact. Is it hard?
It's not hard to see. So it's not hard to see. So let me say something about how you see this. So first of all, we know. So this fact, this is, I guess maybe we talked about this previously. This is this equation here, that the affine algebra of GM to the n is just Laurent polynomials in these chi-i's. That's I guess that's standard. That's yeah, it follows from stuff we've talked about before. And now any Laurent polynomial is yeah, it's a sum of Laurent monomials, and each Laurent monomial is chi-i to the, yeah, it's some chi-i's raised to some powers. And so that's a character. I guess the confusing thing is writing things additively versus multiplicatively. So if we think of it as a function, I guess it's more natural to write it as a product, the monomial as a product of different terms. But if we translate things into characters, into z to the n, then we see that it's a sum. It's a linear combination of these chi-i's. So I guess that's kind of the way to see it. Maybe, yeah, that's the idea. Does that answer your question?
I still don't see everything, but yeah, it's fine. I mean, take a look after.
Yeah. I think the confusing thing is that these Laurent polynomials are written multiplicatively, but the characters are written additively. Yeah, basically every character corresponds to a monomial. But yeah, I guess, yeah, if you think about it and write it out, I think you'll be able to see this pretty easily. Okay, so what about the co-character group? Well, the co-character group of GM to the n is again just z to the n, and this is given, so explicitly z basis is given by the following. So if we take, so we can it's given by including into the ith coordinate. So we have lambda I that defines a map from GM to the n, where we take a in GM to the a appearing in the ith coordinate. All the other coordinates have 0. Okay. So yeah, so that's the example of GM, the torus. In both cases, in both the case of the characters and the co-characters, we get a free abelian group. Okay, now what if we had something else? So let's take a primitive Lth root of unity inside the field K, and let's look at the subgroup it generates. So it's a cyclic subgroup, and in fact, this is a subgroup inside of the multiplicative group. So this Lth root of unity, it's an Lth root of unity of K, but it lies in K star, and so we can think of it as an element in the multiplicative group, and it generates a closed subgroup of the multiplicative group. And yeah, so it's a diagonalizable group. And let's compute its character and co-characters. So what are the characters? Well, we need to compute group homomorphisms from this finite cyclic group into GM. Well, these are determined by where this primitive Lth root of unity goes. It has to go to something that has order dividing L. So it has to go to some multiple of itself. And there's only L distinct multiples of itself. And so we see that the characters are again a cyclic group. So that's just an easy computation. What about the co-characters? Well, okay, so if we have a co-character, that must be a map from the multiplicative group to this finite cyclic group of roots of unity. And the claim is that there are no non-trivial group homomorphisms. There are several ways to see this. One is that the GM, the multiplicative group, is connected. This is disconnected, so it's any group, any map of varieties must map GM to a single point, and since it's a group homomorphism, it must map it to the identity. Or we can think of this any group homomorphism from GM to the cyclic group as further defining a group homomorphism into GM by embedding this cyclic group as roots of unity inside of GM, and then observing that then observing that we have a homomorphism of groups between GM and GM, so it must be of the form x goes to x to the n, but none of these have image contained inside the finite cyclic group unless n is equal to 0. So that's the only possibility, and then we get a trivial homomorphism. So here the symmetry breaks between the characters and the co-characters. Right. Yeah, okay, those are the examples. Any questions about the examples? All right, so again, diagonalizable groups are subgroups of GM to some power. Subgroups, and if we have GM to some power, we call that a torus. So diagonalizable groups are subgroups of tori. All right, so now we have this result about diagonalizable groups. So if we have a linear algebraic group, then we have the following conditions which are equivalent. So first, G is diagonalizable. Second, the character group is a finitely generated abelian group, and its elements form a K basis of the affine algebra of G. And third, any representation of G is the direct sum of one-dimensional representations. Okay, so let's prove this result. So first of all, let's assume we have a diagonalizable group, and let's try to show that its characters form a finitely generated abelian group, and the characters also form a K basis of the affine algebra. So what does diagonalizable mean? It means G is the subgroup of GM to the n for some n. So it follows that GM, so it's a closed subgroup, so it follows that the affine algebra of G is a quotient of the affine algebra of the torus G sub m to the n. So this, in case you can't read it here, this is the multiplicative group raised to the nth power. So we have some ideal here. This ideal obviously has to satisfy some properties for this to be the affine algebra of a group, but we don't care about them. We just need that it's some ideal. And we can...
Sorry, this theorem is the analog of just saying that G is an abelian group, right?
G is an abelian group? Well, I'm sorry, can you elaborate on?
I mean, because if it's diagonalizable, then it's commuting. I guess we didn't really see I didn't really see a clear definition for that in terms of the coproduct. But and any abelian group, all its reps are one dimensional. All its E-reps.
Yeah, that's correct. Yeah, but this is a bit. Yeah, it's related to that. Let me see what this is. So first of all, so any diagonalizable group is abelian. Maybe I don't know if I said that, but that's true. But it's saying something. So for finite abelian groups, we have this thing that any representation is a direct sum of one-dimensional representations. But as we saw with unipotent groups, so unipotent groups, this is not true for unipotent groups. Even if the unipotent group is commutative, it's not every representation of a commutative unipotent group is a direct sum of one-dimensional representation. So diagonalizable is important here. It's not just the commutativity of the group that we're using.
Okay.
Yeah. So, okay, so where were we? Okay, so G was diagonalizable, so its affine algebra is the quotient of the affine algebra of a torus. So this means that this restriction map, so if we have oh, this should be an X star here. So we know that everything in the affine algebra of the torus is a k-linear combination of characters, and that implies that, let's see, that implies that if we take the restriction map, so if we take a character and we restrict it to okay, just give me a second. I don't think this is written very well. Okay, so first of all, let me fix this. So this implication maybe is not completely obvious, but it's true. So this should be the characters. So this is not completely true, but we do have a restriction map. So if we have a map between groups, then there's a restriction map between there's an induced map the other way between their characters. So this is just coming from precomposition. And now the claim is that in this case, this restriction map has to be surjective. And the reason for that is because any character is in particular a affine function, so a polynomial function on G, and so then it's given by it's in the image of this quotient, and so then it's a linear combination of characters. But we see that any restriction of a character is again a character. So if we apply this map here, we again get a character, and yeah, so that shows that this map is surjective. So maybe there's a bit more detail here that might be missing, but I think that's the idea here. So once we know that this restriction is surjective, then we know that this character group is a quotient of z to the n, because we already computed that this character group is z to the n. And we know that based on this quotient map here, its characters have to form a k-basis of the algebra of functions here, because that's true for the characters of the torus. Okay, so maybe this was not very clear. Maybe I'll send an email with clarifications later. Okay, so that proves that the group, that proves A. So the character group is finally generated, a abelian group, and the characters form a k-basis of the affine algebra. Okay, so now how do we go from B to C? In other words, how do we start with this assumption that the characters are a finally generated abelian group and they form a basis for the algebra of functions, and how do we obtain that any representation splits up into a direct sum of finite dimensional of one-dimensional representations. Okay, so let's take some representation. G goes to GLV. So now let's, for concreteness, let's pick a basis of V, and we can extend rho to a map rho bar from G to n by n matrices. So nothing too much going on here, just thinking of this rho in different terms. So now the thing that we're aiming to show is that this V splits up as the direct sum of subrepresentations, and these subrepresentations are indexed by chi. Chi being a character of G. So what is this V chi? Well, V chi will be the set of all vectors V in V, such that the action of G on V is just through the character chi. So any element in the group acts by a scalar on this V. Okay, so these are obviously subrepresentations of V, and these themselves. So if we have a chi, then the group just acts by a scalar. So each element in the group acts by a scalar on V. So V chi just splits up as one-dimensional. So if we pick any basis for V chi, then the span of that gives us a decomposition of V chi into one-dimensional subrepresentations. So once we know that we have this equality, then we're done. Okay, so what will be going on here is that these one-dimensional irreducible representations that we want to split the representation into, these are indexed by the characters of the group. All right, so this is what we're aiming to show. So let's go back to this map rho and the map rho bar. So if we look at the induced map on the algebras, so rho bar star goes from the affine algebra of n by n matrices to the affine algebra of G. Okay, so now we use the fact that the character lattice of G, which I'll denote by just X, we use the fact that our hypothesis that forms a K basis of the affine algebra of G. So that means that anything we take here, so anything we take in this affine algebra of matrices, and we send it over here by this algebra homomorphism, we can write in terms of characters as a linear combination of characters. So in particular, yeah, so that's, I guess, what I just said this. So if we take F in the affine algebra of n by n matrices, we can write F as a linear combination of characters. So these F sub chi's, those are scalars. Those are in the field K. All right. And these are uniquely determined because we have a basis, and finitely many of them are non-zero. All right, so which F's do we want to take? Well, inside this affine algebra, we have some distinguished elements. We have for each I and j, between I and j both running between I and j, 1 and n, we have the coordinate function for the ij entry, so row I and column j. So, and those generate this affine algebra of the matrices, of the space of matrices, as an algebra. Those generate this algebra. So we also want to take the elementary matrix corresponding to I and j. So that's a matrix. So yeah, that's a point in the space, whereas Tij is a function on the space. Okay, so now let's do the following manipulation. So this may seem a bit weird at first, but it all comes together in a bit. So if we take little g inside the group, we apply rho bar. So that's a matrix. Well, any matrix we can write in the following way. We can write it as a sum of elementary matrices. So And what is the coefficient of the elementary matrix Tij? Well, it's the value of this function, the elementary matrix Eij. Well, the coefficient is the value of this function Tij applied to our matrix. So we take this matrix, we apply the Tijs, those are coefficients for the Eijs. Okay, so that's kind of maybe kind of obvious, but now what we want to do is the following. So we think of these. So what's happening here is that we're taking G, we're applying this map rho bar, and then we're applying a function Tij. So just thinking about what this means, this is the same as pulling back the function Tij to a function on G and evaluating at G. So this is just different notation. And we're still taking the sum over I and J running from 1 to n. But now we use this fact about characters forming basis for the affine algebra of functions on G. And so we can write this Tij, we have some coefficient here, Tij. So we can write this pullback. So what's happening here is we're writing this pullback as a linear combination of characters where the coefficient of the character chi is Tij sub chi. So this is just notation. This is just some scalar. And we're evaluating a G, so that means we're evaluating all these characters. Okay, and so now we just rearrange the sum. So we sum over characters, chi G, and then we have this new matrix here. So this is just a matrix because we have some coefficient for each Eij. And yeah, this is some matrix. We call it A sub chi because it depends on how these functions Tij transform under rho, and the coefficient their coefficient when we decompose it as a linear combination of characters. Okay, so this is just some matrix A sub chi, and we see that we can rewrite this as a sum over characters of these A chi's with coefficient chi of G. So remember, so let me just scroll back up here. We started with rho bar of G, and we wrote this rho bar of G as a linear combination of some other matrices, A chi with coefficient chi G. So actually these A chi's are kind of determined by the representation, and for different G's we just put different coefficients on these A chi's. All right, so this is a computation. And so now that we have these matrices A chi, there's a few things to check. So first of all, if so these A chi's turn out to be projection matrices, so they're orthogonal, and so if we take two of them that are different, then we get 0. So they're orthogonal. But if we take A chi times itself, so if we compose these two matrices, then we just get A chi back. So these are idempotents. They're orthogonal idempotents in this matrix algebra. And their sum, if we take the sum, then we just get the identity. So yeah, so these are things to check. So I won't spell them out for you. You're welcome to go through the formulas and check. Let me just give some idea of why they're true. So this first one, it comes down to the fact that the characters are group homomorphisms. So yeah, so you use the fact that rho bar of G times H is rho bar of G times rho bar of H. And then you see how this translates to things about the characters and yeah. So it's just, you write everything out and then it becomes clear. And why is this true? Well, this is this fact about the sum of the chi's, the A chi's being the identity. That's just the fact that the identity of the group acts by the identity on the vector space. So it's the identity matrix. So that's actually kind of immediate from the equations that we just saw. Okay, so, and there's one more thing, which is that the image of A chi is this subspace V chi that we saw before. So this is the, V chi, just to remind you, is the set of all vectors that transform under the action of G by this character chi. So, so the fact that we have these, so anytime we have a vector space and inside the endomorphism of the vector space, we have orthogonal projectors, orthogonal idempotents, whose sum is the identity. we have that the vector space decomposes as a direct sum of the images of these projectors. And so we get that V is the direct sum of these V chi's. Okay, and and then as I said before, that this V chi is a direct sum of one-dimensional representations determined by this character. Okay, so I think this is a good place to stop for a break. So let's take a 5-minute break, and we'll take it from there. I'll ask for questions once we start again. So I thought about this proof here. So A implies B, so G is diagonalizable. So what's going on here is the following. So if you have, so first of all, we have this fact that this restriction map has to, okay, let's leave this fact aside. We have that we have a restriction map. We don't know yet that it's rejected, but it will turn out to be rejected. But we do have a restriction map. So any character of the torus restricts to give a character of G. And now, if we want to show that the span of the K span of the characters of G is all of this affine algebra. So if we take any function here in this affine algebra, any f, then we know that it's in the image of this map here, and we know that the characters here, if we map them to kg, then they span all of kg because this map is surjective, and because they span all of k of the torus. And so if we have a function, we can write it as a linear combination of images of the characters here. But all those images are themselves characters of G. And so then any function is a linear combination of the characters of G. So that's the idea there. So I kind of, this is not really clear what I wrote, so I'll write this again and send you guys an email. All right, so and then we also talked about the proof B implies C. Any questions on the proof so far? This is the theorem. Okay, so we proved that A implies B, and we proved that B implies C. So now it remains to show that C implies A. But actually, that's the easiest step. So how do we prove that C implies A? Well, let me just scroll down here. So we assume that, so first of all, we embed G inside GOV. And so now we know that, so when we embed G inside of GOV, that means that V is a representation of G. So by our hypothesis in part C, there's a basis So we can decompose V into a direct sum of one-dimensional representation. So what that means is that we can choose a basis of V where G acts diagonally. So if choosing a decomposition into one-dimensional subspaces of a vector space is the same as choosing a basis up to scaling. And so if we write that, and if all these subspaces are subrepresentations, G preserves them, then in this basis we have that G is a diagonal matrix. Yeah, so then D embeds inside of diagonal matrices, but diagonal matrices form a torus. So that means G is diagonalizable. Okay, so yeah, I hope that makes sense. So this is kind of one of the main results about diagonalizable groups, and it shows that their representation theory is governed by these characters. Okay, and also what we see from this theorem is that so this is this corollary that if G is diagonalizable, then the group algebra of the abelian group of characters is isomorphic to the affine algebra KG, and that's coming from the fact that these characters form a K basis for the affine algebra, and their multiplication is compatible with the multiplication on their multiplication in the group algebra is compatible with the multiplication in the affine algebra, so we get this isomorphism. All right, so what's next? Okay, so by the way, in the book, there's things about what happens in positive characteristic, but for the purposes of this class, you can just assume that the characteristic is equal to 0. So the characteristic of the underlying field K, which I'll remind you is algebraically closed, we can just take that to be characteristic 0. So in this case, we have a bijection between diagonalizable groups and finally generated abelian groups, and this bijection is given by taking characters. So anytime we have a diagonalizable group, we can just take its characters. That completely determines the group. So this is a bijection. So let me kind of give you the idea. Maybe I won't prove all the details here because it's a matter of just checking some things. But what's the construction? How do we take a finitely generated abelian group and produce a diagonalizable group? Well, this is the construction. So if we take M to be our finitely generated abelian group, then let's take its group algebra. And just this is notation. E sub M will be the basis element of the group algebra corresponding to little m inside of M. So these multiply, so EM times EM prime is EM plus M prime, if M is written additively. All right, and so now that we have, this is, the group algebra has its algebra structure, but we can define a Hopf algebra structure on the group algebra by the following formulas. So this is kind of like diagonal here. So we take EM and map it to EM tensor EM. And so that's the coproduct. For the co-unit, we take each of these EMs to 1. And for the antipode, we take EM to E minus M. So this corresponds to taking the inverse, the additive inverse, which is just the negative. Okay, so that's a Hopf algebra. And so now the claim is that this K brackets M as an algebra, it's affine algebra, so it's finitely generated. We know that because the abelian group was finitely generated, and it's also reduced. So you can check that. I guess one way to do it is to look at the classification of finitely generated abelian groups, and you can check that this algebra is reduced, no non-zero nilpotents. And because we have a finitely generated reduced algebra, in other words, an affine algebra, there's an associated affine variety. But now we also have a Hopf algebra structure on this K brackets M. So that means that this variety that we get is in fact a group, linear algebraic group. So as a result, we get a linear algebraic group whose affine algebra is equal to this algebra of functions, group algebra of M. So here, so the notation maybe is overloaded, but so here, but on the left-hand side, we mean the affine algebra of an affine algebraic variety of this linear algebraic group. And on the right-hand side, we mean the group algebra of the finitely generated abelian group M. Okay, so in fact, yeah, so by definition, these are, by the choice of G, these are isomorphic as Hopf algebras. And so now it's a matter of routine checking that G is in fact diagonalizable, and that the characters of G are isomorphic to M. So in fact, it's easier to show first that the characters of G are given by M, and then the fact that G is diagonalizable follows from the theorem we just proved. So let me just give you an idea of how this last thing works, why the characters are identified with M. So the idea of the computation is the following. So we take the group homomorphisms from G to GM. So those are the characters, and now those are the same as the Hopf algebra morphisms from K brackets T plus or minus 1, so Laurent polynomials in one variable, because that's the affine algebra of GM, to K brackets G. So we saw previously that for linear algebraic groups, so groups that are affine, for whom the underlying variety is affine, that their everything about them is determined by their affine algebra functions. In particular, group homomorphisms between linear algebraic groups are equivalent to Hopf algebra homomorphisms between their affine algebras. So then we chose G so that its affine algebra is the group algebra of a fixed finitely generated abelian group M. So we're looking at Hopf algebra homomorphisms from K brackets T, from Laurent polynomials in one variable to K brackets M. And the claim is that these are determined by the following. So T has to go to one of these E sub N's. So there's I guess the easiest way to see this is to kind of argue, or I don't know if it's the easiest way, but one way is to use the structured theorem for finitely generated abelian groups, and to argue that yeah, so it comes down to, so when we proved this fact that group homomorphism from GM to GM is equal to the integers, we needed some facts about units inside of some Laurent polynomial algebra. We proved as a lemma that the units of this algebra of Laurent polynomials are given by the monomials T to the N for N an integer times some coefficient. So using that fact, so that fact comes in here. And yeah, you can also think about it in terms of the coproduct, because this is a Hopf algebra homomorphism, so it has to respect coproducts. And we know that the coproduct of T is just T tensor T. And that's also, and the coproduct of E sub M is also is of a similar form, it's just E sub M tensor E sub M. And in fact, these E sub M's are the only elements that have this structure in their tensor product up to coefficients, but then we use the co-unit to show that those coefficients have to be 1. So yeah, so I didn't spell it out here, but it uses ideas that we've already seen. And then, as I said before, once we know that the characters are given by just M, by the finitely generated abelian group that we started with, then we use part B of the theorem to show that G is in fact diagonalizable. Right. So yeah. So just a few more things about this dictionary. So now we justified this dictionary, and if we kind of elaborate, if we dig into the details of the construction, well, we don't have to dig very deep to see that there's a certain class of diagonalizable groups that's kind of nice. So these are the tori, so GM to the n for a non-negative integer n. So these are in fact exactly the connected diagonalizable groups. And yeah, so that's a particular class here. And those correspond to the free finitely generated abelian group. So Z to the n for various n. Yeah, so diagonalizable groups that are not tori are a product of a tori and an abelian group, a finite abelian group. And so yeah, so and that finite abelian group appears here as a finite generated abelian group that's not free. Right. So yeah, so that's how this dictionary works. So this dictionary sends tori to Z to the n. So for tori, we'll call this Z to the n that we get the character lattice. So it's a lattice. It's a free abelian group, and we have the character lattice for any torus. Okay,
Did you
so
prove?
I think.
Did
Sorry?
you prove the whole table? Like what? How do you know that connected diagonalizable groups are the toris? How do you know this?
So I guess
Proof?
one way to do it is, yeah, okay, let's see. Yeah, maybe this requires a bit of argument, but I think if the group is, let's see, yeah, okay, maybe there's something to show there. I think it definitely follows from the things that we've shown, but maybe there's, yeah, I mean, it comes down to the fact that if we have a diagonalizable group, then it's basically a torus cross a finite cyclic, or like a product of finite cyclic groups, because the only subgroups of GM, the only finite subgroups of GM are the cyclic ones, or I guess, yeah, cyclic ones, and then you go from there. But yeah, okay, maybe there was something more to show here. Okay. So, yeah, any other questions about this dictionary? Yeah. So let's move on. So, okay, now we have this result about the rigidity of diagonalizable groups. So somehow, yeah. So so let me first state it, and then I'll explain why it's called the rigidity of diagonalizable groups. So if we have two diagonalizable groups, G and H, and we have a connected variety V, then let's suppose we have a morphism of varieties from V cross G to H, such that for any little g, oh sorry, yeah, for any little v, the map from G to H that we get by the following formula. So we fix the v, we fix our v, that gives us a map from G to H by this formula. And we suppose, so our hypothesis is that this morphism of varieties is such that each of these maps is a map of algebraic groups from G to H, from these diagonalizable groups. And this is true for every little v. And then the result is that this morphism is actually independent of v. So it's just determined by what happens on the g factor. So somehow we can't, if we start with so the reason why this is called a rigidity theorem is because if we start with a homomorphism of groups from G to H, then we can't deform it somehow in a non-trivial way. We can't construct some interesting family of homomorphisms. So we think of this phi here as a family of homomorphisms from G to H, and this family is parameterized by this connected affine variety V. And the result is that this family is actually the trivial family. Okay, so let's see. How does this work? So first of all, if we have this morphism of varieties, we get an algebra homomorphism from the affine algebra of H to the tensor product of the affine algebra of V and the affine algebra of G. Right, so that's standard. So now if we take a character of H, then we can write it as in the following fashion. We can write it as a sum over characters in G, f, so some function on V, some element of the affine algebra of V, tensor chi. So this is using the fact that G is diagonalizable, so that it's these characters form a basis of the affine algebra of functions. So we choose that basis here. So anything in this tensor product can be written as in terms of that basis. So we put the chi's and we have some function here. So sometimes this function is 0, but yeah, I guess it'll be 0 for it'll be non-zero for only finitely many chi, but we have something there. And right, so this is the pullback of psi is written in this form. And so now we have to argue a few things. So first, we have to show that this map that takes G to the evaluation of this so we fix our V and we fix a V and we evaluate this F at V. And now the map that sends G to the evaluation of this resulting map, the resulting element of the affine algebra of G at little g, we argue that that's a character for any little v that we chose. And here psi is fixed. So we fix our psi. And then we basically take this and we apply little v here and little g here. And we think of this as a family of maps on G indexed by V. Okay, so that maybe made it sound more complicated than it is, but it's just this formula. And so the reason this is true is it comes down to the fact that this phi this homomorphism phi that we had at each, when we fix little v like we're doing here, then that phi as a map from G to H is a group homomorphism. So from that we get that this is a character. And the second thing we need to argue is that if we fix our psi inside it's a character on H, then there's a unique character of G, so I'm going to call it chi sub phi. So it's determined, it's a character of G and it's determined by this psi, so that's why I have a little psi here. So there's a unique character of G such that this coefficient that we had, so this coefficient up here, is equal to the constant function 1 on V if this character is equal to chi sub psi, and it's 0 otherwise. So yeah, so this, let me see, okay, so the reason, so this is something I guess I'm not going to show in detail, but the reason for this is the fact that these that the psi's and the chi's form bases for their affine algebras of functions. Yeah. So right. So then, yeah. So then, what that means is that if we go back, so if we take this fact here, that comes out that comes from the results about bases. If we take this fact, then when we go up to this formula here, we see that the pullback of psi under phi is just, there's only one term that appears here. There's only one thing that we're summing, and it'll be the chi sub psi, and that will be the constant function 1 as its sort of coefficient in the k brackets v factor. And yeah, that pretty much does it. So so since yeah, so then okay, so then yeah, so this is true for the characters yeah, this is true for the characters of H, but then we show that it's in fact true for any linear combination of the characters. We just get this factor of 1 here. We will get some other things over here, but we still keep this factor of 1. And so for any function, function on H, for any element of the affine algebra, we just get that this pullback is 1 tensor some function on G, and that gives the result. Okay. Any questions here? So let me go back to the statement of the result.
Again, where is the step that you say that V is independent? It's independent of V in the proof?
Yeah, so it's yeah, it's in this step here. So okay, so let me try to say a bit more. So since this map is a character, it must be equal to some chi. So that's this chi sub psi here. So we fix our psi, we get this map from this function on G. So it's a map from G to GM, and it's a character for any V in V. So that means that this is a character. We're going to call that character chi sub psi, right? So this and so now this character, yeah. So then this character, this function is just a character. It depends only on psi, not on V. Okay, so yeah, I guess there's yeah. So there's so the fact that we also need to use the fact that V is connected here. So there's a map from V to the characters that sends little v to this character, and since the characters this is a continuous map, the characters are discrete topological space, so it must be sent. They must all be sent to the same character, and that's this character chi sub psi, and this is true for any little v. So that's why this is a constant function.
And how did we prove that the characters are discrete in the sense?
Yeah, well, because it's a diagonalizable group, so its characters are finitely generated abelian group, and yeah, that's how. Does that make sense?
What is the relation between the topology to the abelian groups? I didn't understand. How do you know that this?
Well, it's so the map is, I mean yeah, okay, let me delegate this to, maybe I'll send you an email or something. Let me delegate this to an email discussion. Yeah, so I'll answer your question, but maybe not right now, so that we can move on. Yeah, any other questions? Okay, so let's see how much time. Okay, so now, okay, let me give a little application of this result. So if we have a group G, so G is some algebraic group, and H is a diagonalizable subgroup of G, yeah, I think G also has to be a linear algebraic group, not just any algebraic group. So then the connected component of the normalizer of H inside of G is equal to the connected component of the centralizer of H inside of G. And moreover, this quotient of the normalizer by the centralizer is finite. So yeah, I mean, I guess you guys are all familiar. So normalizer is all the elements in G that send X to itself under conjugation, and Z is all the things that fix H point Y, so that commute with all the elements of H. And then this centralizer, so the centralizer is always contained in the normalizer, and we have that. Yeah, so, okay, so the claim is that this is finite in this case. Well, we just apply the previous result to the following map. So we take the connected component of the identity inside the normalizer. So that's the connected variety. We take H and we take this conjugation map. So this is so for any G, this map from H to H that we get is a map of varieties. Sorry, it's a map of varieties, but it's more importantly a map of groups, map of algebraic groups. Yeah, and this is a connected, we took the connected component of the identity, so this is connected. So that's how we get this result. Right, so now, yeah, so now at this point, there's some exercises in Springer, and for those exercises, I'll tell you which ones are eligible for submission and which ones are optional, but for those exercises, you can assume that the characteristic of the field is equal to 0. Right, so let's see, is this? Okay, so let me just say a few more things. I think we're almost out of time and we're almost done with these notes. So let me just say a few more things. So let's focus on the case of tori. So if we have a torus T, I'm gonna set X to be the character lattice of the torus and Y to be the co-character lattice of the torus. So first of all, there's a pairing Y cross X to Z. So what is this pairing? So it's coming from the definitions. So if we have a co-character and a character, then what we can do is we can compose them so that we produce a map of groups from GM to itself. So we start at GM, we apply lambda, then we apply chi, and we land back in GM. So this composition will be a group homomorphism from GM to itself. And we already showed that the group homomorphisms from GM to itself are just indexed by the integers Z. So this is corresponding to some integer. So in other words, lambda of A, then if we do lambda of A, then apply chi, that's just raising A to some power. We call that power this pairing of lambda and chi. Okay, so anytime we have a pairing like this, we have induced maps. So X goes to the group homomorphisms from Y to Z, and Y goes to the group homomorphisms from X to Z. And this is just by, evaluating. So we can plug in Y in this first factor and then apply this pairing at chi. Or here we plug in lambda in the first factor and then apply this pairing for any chi. So that's pretty straightforward. And so in fact, this pairing is a perfect pairing, which means these two maps are bijections. And moreover, there's a in this case, there's a canonical isomorphism between the extension of scalars of y to the field we take k star to the multiplicative part of the field to the multiplicative group of the field, which is the commutative group, an abelian group. So we extend the scalars, and what we get is just t. And this map is given by the following. So if we take A, which is something in the field, which we can think of as GM, and we take lambda being a co-character of the torus, and then we just apply lambda to A. So then we get lambda is a map from GM to the torus. So if we evaluate at A, we get something in the torus. The claim is that this is an isomorphism. And so to prove this lemma, it's enough just to do it in the case where we've picked an identification of T with GM to the n. And in this case, the character lattice, as we showed before, and the co-character lattice are both z to the n. And if you work out what this pairing is doing, it's just a dot product. So we take x, a vector in z to the n, or a point in the lattice z to the n, x1 through xn. Y is a point in the lattice z to the n, y1 to yn. And if you go through the definition of what this pairing is doing, we see that what we get in the end, the integer that we get in the end, is just this dot product of these two vectors, or of these two points in the lattice. And we know that the dot product is a perfect pairing between on Zn, and so or if you haven't seen this, then it's easy to show. And then it's kind of the same thing for this for the last fact. We think of, so y is just z to the n. So if we take this tensor product, k star tensor z with y, then y is just z to the n. And so then we're taking k star tensor over z with z to the n. That's n copies of k star, which is n copies of the multiplicative group, which is t. So I guess this is kind of clear, but both x and y are free abelian groups when T is when the linear algebraic group in question is torus. Okay, so I guess that's it for the lecture for today, but I'm happy to stick around for another few minutes and answer any questions that you have. Maybe I can also answer Tal's question. Okay. Oh, thanks.
I have a question.
Sure.
Are there more connected abelian algebraic groups that don't come from GM and GA?
Say this one more time.
Are there more algebraic abelian groups that don't come from GM and GA?
In some sense, it depends what you mean by come from.
Like products.
Then yes, then there are other ones. But if you take so I mean, okay, I forgot how you asked the question, but the fact is that if you take there are commutative unipotent groups that are extensions, non-trivial extensions of GA. So those groups are not just products of GA. you have some extension. So for example, if you take the group of UN of unipotent upper triangular matrices, that's a successive extension of additive groups.
But it's not abelian.
Oh, but you asked for abelian. Okay, for
Yeah,
abelian,
I'm interested, what are the abelian groups?
you asked for abelian. Okay, so for abelian ones, you have, so first of all, we had this result that it's the product of the semi-simple part and the unipotent part. So the semi-simple part, we, I guess, more or less discussed. Yeah, we discussed that. So that part is covered. And the unipotent part, so yeah, I suspect that there are unipotent groups that are not just the product of additive groups, but I don't have an example off the top of my head.